So I want to work this example. I want to do it 3 different times, one with each method. So I'm going to start with the LevelSet method. Now I have this vector field, so imagine there's some fluid that's flowing and its velocity is described by this vector field. And I've got this surface, z minus x minus y equals 0, with some bounds on x and y. So have it as a level set. And I want to find the flux of this fluid through the surface in a particular direction, just so that we know which normal to choose. And we're going to use the LevelSet method, and we're going to project down the j-axis. So we have this function, and just because we have Maple, I thought I might as well graph the function so you can look at it. So looking at the function, this is the function here. So I've graphed that LevelSet. You can see it's really just begging for me to project down the z-axis, because if you look down on the z-axis, of course, x is between 0 and 1, and y is between 0 and 2. I can't quite rotate this just right. Okay. But that's just going to be a nice rectangle if I project down the z-axis. But just for fun, I said, well, why don't we project down the j-axis and see what region that we get. So we're going to project down the j-axis in this case. Now what we need to do is to figure out bounds on this region. So we can see we can easily put x between two constants, and that's going to be between 0 and 1, and then we just need to find bounds on z. Those are going to depend on x, since both the upper bound and the lower bound depend on your location x here. So we've got to set up the region, we've got to get our conversion factor, then we can set up the integral and do it. Okay, so we've got z minus x minus y, right? And we know that x is between 0 and 1. And we know that if we project down the z-axis, then we're looking at, remember our surface here, it came out something like this, right? And these two both projected back to be vertical lines along the z-axis. So, and then it's this boundary here and this boundary here that we want to figure out what is their shadow here in the xz plane. So let's see, this boundary satisfies the equation z minus x minus y equals 0, or z equals x plus y. But along this boundary, we're out here at the end where y is equal to 2. Remember, y goes from 0 to 2. And this is going to be highest where y is equal to 2. So we have z equals x plus 2. That's the shadow then here in the xz plane. On the other hand, at this boundary, we have y equals 0, right? So this edge here is actually already there on the xz plane, and it's just where y equals 0. So if z equals x plus y, because we're on the surface, but we're at the location on the surface, the location's on the surface where y is 0, then we just have z equals x. So we get bounds on z then. Z, if we look back here in the xz plane, remember we saw those two parallel lines, we just figured out that x is between 0 and 1, and z is between this line and that line for each value of x. So z goes between x and x plus 2. So we've got the bounds of our region to integrate over. That's a step forward. Now what we need to do is to get a conversion factor so that if we have a little patch of area here in the shadow, when we project down the y-axis, how do we get the actual area of the patch on the surface? So, well, when we have it as a level set, then the conversion factor is the gradient of f divided by the length of the gradient of f dot with the projection direction p. So our function f here is the thing that's set equal to a constant. It is z minus x minus y. So the gradient of f is -1, -1, 1, because the partial with respect to x is -1, partial with respect to y is -1, and the partial with respect to z is 1. So the length of the gradient is the square root of 1 plus 1 plus 1, which is going to be the square root of 3. And let's see, the absolute value of the gradient of f dotted, dotted with our projection direction p, well, we're actually dotting it with j because we're projecting down the y-axis. And j has components 0, 1, 0. So when you dot them, you just get 0 times negative 1 plus 1 times negative 1 plus 0 times 1 makes negative 1. So it's the absolute value of negative 1, which is 1. So therefore our area conversion factor is gradient f over 1, which is square root of 3 over 1. So there's our area conversion factor. The next thing that we need to do is to set up our normal, right? But to get the normal, we can just use the gradient. We need to make sure that this gradient is in the correct direction. So at a point on this surface, this is moving back in the x direction and back in the y direction and up in the z direction. So I can see that's the normal that's moving back towards the z-axis. And this normal out here, the opposite of gradient of f, so negative gradient capital F, is going to be the one that's moving out. So this is the correct direction for that normal. If it wasn't, I'd just flip the signs on all of these. Okay, so I've got to set up my integral. Remember, to do a flux integral, you have to go around the surface, adding up the vector field. This is bold F, not to be confused with just capital F, which is my LevelSet function. Bold F dot n d sigma. But we convert that to an integral over a region in the xz plane. We're having x run from 0 to 1 and z run from x to x plus 2. And now I need to write my vector field f here. Well, if I'm in the xz plane, I know what my x is. So that's going to be x squared and that's going to be z. But I need to figure out what the y value is. But I can solve this equation for y to get y in terms of z and x. So since z minus x minus y is 0, y is z minus x. So now what I've done is I've written my vector field bold F in terms of in terms of x and z. So in terms of the location within the shadow here. Now I dot it with my unit normal, which is going to be negative 1, negative 1, 1 divided by the square root of 3, right? So there's my unit normal. And then d sigma, I have my conversion factor, which is the square root of 3 times the area in the shadow, which is dz dx. So notice that this area conversion factor and the length of the gradient, of course, are the same, so they're going to cancel. So I end up with the integral from 0 to 1. If I calculate this dot product, I have negative 1 times z minus x, so that's x minus z, minus x squared, plus z. Oops, I forgot my inside bounds. X to x plus 2. And I just need to integrate that with respect to z and with respect to x. So the integral from 0 to 1 and the integral from x to x plus 2. Let's see, we have a minus z and a plus z, so actually I just need to integrate x minus x squared with respect to z and then with respect to x. Now this is a pretty straightforward integral. Let's just go ahead and finish it off. This is constant, so the x minus x squared comes through, and then we have the integral from x to x plus 2 of dz and all of that dx. But let's see, the integral of dz is just 1, the integral of 1 dz is just z. We plug in x plus 2, we plug in x, we find the difference, we just get 2. So we have 2 times integral from 0 to 1 of x minus x squared dx, and so we have 2 times antiderivative would be 1/2 x squared minus 1/3 x cubed. And we just evaluate that antiderivative between 0 and 1. And so we have 2 times, let's see, 1/2 minus 1/3. We plug in 0, you don't get anything, so there's nothing to subtract on the lower end. And 1/2 minus 1/3 is a sixth. 2 times 1/6 is a third. And that's the flux through that surface.